So far in chemistry, we have looked mostly at the atomic level, where we bring atoms together to bond, to form compounds. Some atoms like to stay apart. Some of them will share electrons to make bonds, or some of them will give and take electrons instead. But in whatever case, we're typically looking at kind of the zoomed in version, down to the nitty gritty between atoms. Something so tiny that we can't even begin to imagine how small it is based on our world experiences. But when we get into the lab and we want to do chemical reactions, we have to deal with amounts of chemicals that we can actually see and measure. Otherwise, we lose kind of the point of making observations, and we have a lot harder of a time making measurements, like how much, okay, or how hot, how cold, things like that. So we need kind of a bridge that takes us from the world of atoms to our world, what I like to refer to as macroscopically, okay, where if you think like microscopically would be very, very tiny, or nanoscopically would be even smaller than that. Macroscopic is kind of our world. It's the big stuff that you can get your hands on, okay? So if we want to be able to talk about atoms and molecules and compounds and things, the stuff that we know about in the world of atoms, but be able to translate it into what we deal with in the lab, this kind of bridge that brings us from one to the other is a concept, or rather a unit, called the mole. Okay? A mole is just a number. It's kind of the chemist's dozen, and you'll hear that a lot and see that a lot if you go and find other videos and lessons and things like that. Okay? A mole is just a number of particles that brings us from the atomic world up to the scale that we can see and feel and deal with, like this aluminum powder here. Okay, so this is 1 mole of aluminum powder in this test tube. Okay, just like how a dozen is 12, okay, or a pair is 2, a mole is just a number of things. Okay, and typically in chemistry we use it for atoms and molecules and things like that. Okay, specifically a mole is 6.02 times 10 to the 23rd things, and that number is going to come in kind of more handy later. But for now, we're worried more about the mole being just a very, very large amount of things, so that we're dealing with an amount that we can actually, observe in the lab and measure. Okay, by the time you have 6.02 times 10 to the 23rd atoms or molecules of something, you start dealing in amounts that you can, actually measure pretty easily. Okay, using something like a mass balance like this, or a graduated cylinder, or something like that for liquids. But why this specific number? Like it's a big, nasty, terrible number, 6.02 times 10 to the 23rd. Why this specific number? Why did we settle on that and not something that looked at least a little bit nicer? Like, okay, yeah, it's got to be a big number, but why not something like 1 times 10 to the 23rd or something like that? Okay, well, 6.02 times 10 to the 23rd has a pretty significant purpose, okay? It just so happens to be that when we have this many particles of something that we call a mole of something, we go from the atomic mass of something to the macroscopic mass with the same value but a different unit. Okay, where's my orange marker? There we go. Same value but different unit. Okay, so for example, I have this aluminum in this test tube again. Okay, so again, this is specifically a mole of aluminum powder in this test tube right here. Okay, 1 mole. In other words, 6.02 times 10 to the 23rd atoms of aluminum. Okay, each atom of aluminum has an average atomic mass of 26.98 AMU. Okay, which basically means if I just go grab a single atom of aluminum, okay, on average, based on the isotopes and the abundance of each of those, it's probably going to have a mass of about 26.98 AMU, atomic mass units. That's how we measure very, very, very tiny things. But AMU is way too small for something in the lab. We measure in grams, okay? So instead, when we have a mole of aluminum, we still get a mass of 26.98. But instead of it being in AMU, it's now in grams. We get the same number. And that's why we need this particular number of particles. It makes our lives a lot easier because there's no complicated conversion in between them. Moles takes us from the atomic mass unit into grams. Right there, same number. So we have a special name for, if I can find this, there we go, for this relationship between moles and the mass of something that we can measure in grams. We call it the molar mass. Okay, you got kind of the mole word in there, molar, okay? The mass of a mole of something, okay? So the molar mass is just how many grams of something you have in 1 mole of something, okay? Like my aluminum, which in 1 mole of aluminum, I have 26.98 grams. So this number down here at the block, at the bottom of the block for an element is not just the average atomic mass, it's also the molar mass. Same thing. So instead of measuring it with a unit of AMU, it comes out as how many grams there are per mole of that stuff. Okay, aluminum has a molar mass of 26.98 grams per mole. It's kind of like that number is doing double duty. It works both ways, whether we're dealing with single atoms or up to moles of stuff. Okay? If we don't have exactly 1 mole of something, like, if I had pour some of this out, okay, we could also use this number to calculate exactly how many moles of a chemical we had. Or vice versa, if we knew how many moles we had, we could use this to calculate how many grams there are of that chemical. Okay, now you might notice it looks like I dropped an E here. It should be like this. Okay, but that's actually how we shorten the unit. It looks kind of odd because we only lose 1 letter. But the mole, okay, just like any other unit, has an abbreviation, just like how grams has an abbreviation, G, or atomic mass unit is AMU. The mole is just MOL. Again, it doesn't really save a lot of space, but it works. It gives us the right idea. Okay, so a mole takes us from the atomic mass to the mass that we measure in the lab in grams, gives us the same number that we would expect. Okay, the only difference is now we're dealing with an actual amount that we can do something with. Okay, and this relationship is what allows us to do all kinds of things in chemistry, especially when we're trying to predict the outcome of chemical reactions. Okay, in this lab, we're going to do a little bit of digging through the periodic table to look at what elements have what molar masses. Okay, and what that means if we have a mole of that element. Like, for instance, if I do not know what this element is here, but I know I have a mole of it, and I go and put it on a scale, I measure out the mass of the stuff inside here, and it turned out to be 32.07 grams. Okay, well, that means that in a mole of this, I have 32.07 grams, so the molar mass is 32.07 grams per mole. So there should be an element or something out there that has a molar mass down at the bottom of the block that says 32.07 grams. For an element, this is super easy because we just go find the element block like that. Okay? For compounds, it gets a little bit trickier because there are different ways we can combine atoms to make higher and higher molar masses, but we'll get to that too. Okay? So we're going to work on figuring out what element is what based on its molar mass, how many grams there are in 1 mole of something, and we'll also look at doing it for compounds as well. We'll have basically a list of 6 compounds, and we'll be matching them up to some of the measurements that we have here in grams. All right, let's look at some examples of elements and see if we can identify them based on their molar masses. So all 6 of these elements here are each 1 mole of that element. Okay, so whatever this is 1 mole of something I can find straight off the periodic table. It's not a compound, it's just a regular element. Okay, and there's exactly 1 mole of it, 6.02 times 10 to the 23rd particles. Okay, that means that if I can figure out the mass of it, I can just find the mass of that 1 mole, the molar mass, on the periodic table to identify it. Okay? Since we're just kind of doing this via video, instead of actually doing mass measurements and trying to put them out on a scale and stuff, we're just going to talk through them. So this test tube here, element 1, okay, contains this kind of dark gray powder. This is, again, a pure element. There's 1 mole of it, okay? And if I go and measure this on a scale, there are 24.31 grams of stuff in here, okay? 24.31 grams of this element, and there's 1 mole of it. That means that this element has a molar mass of 24.31 grams per mole. If I go and look on the periodic table, and I can kind of try and find something that has a molar mass of 24.31, so that's too high. Let's go back over the left side. Hey, there's one. Magnesium has a molar mass of 24.31 grams per mole. Okay, so this element is magnesium. Let's do the next one. This is element number 2. It's kind of a dark brownish powder. Let me see if I can get it to focus. All right. So there is also 1 mole of this element in here. All right. Its mass is 55.85 grams in this 1 mole. So this element has a molar mass of 55.85 grams per mole. So if I go find that element on the periodic table that has a molar mass of 55.85, oh, it's right in the middle. There it is. Iron has a molar mass of 55.85 grams per mole. Okay? Each atom of iron would have a mass of 55.85 atomic mass units. And when I have 6.02 times 10 to the 23rd atoms of iron, okay, and I scale that up to our world, we end up with the same mass, but now in grams instead of AMU. Okay, so in 1 mole of this stuff, it would weigh 55.85 grams. So element 2 is iron. Let's do 1 more of these. Ooh, this is a heavy one. Okay, so this guy, oh man. Shake that around, you can hear that. This guy has a mass of 207.2 grams in 1 mole of this element. Okay, so for this 1 mole here, it's got 207.2 grams, so this has a molar mass of 207.2 grams per mole. So to identify it, I just need to figure out what a single element has a molar mass of 207.2 grams per mole, which, okay, all these are way too small. Oh, that's getting, there we go, down near the bottom. Lead. Lead has a molar mass of 207.2 grams per mole. Now, this might seem a little too convenient for you. Like, it might be like, okay, well, is this really realistic? Now, realistically, a lot of times we won't actually have exactly 1 mole of something in the lab. So this is just to get the point across a little bit easier. But the molar mass is a very useful quantity, and we're going to use it a lot as we go through chemical reactions, because it can help us basically act as a conversion factor between grams and moles. So usually this is kind of not going to be so ideal. It's not going to be so picture perfect. But this is hopefully getting the idea across. The relationship between grams and moles and AMU is hopefully kind of sticking together. Now let's look at some tougher ones where it's not just pure elements, but compounds. Okay? In other words, we have multiple atoms of different elements stuck together. We have to try and figure out, what their molar masses are. Okay. Let's start over here with this example. So, just to recap, if I had the element hydrogen, okay, and I had just 1 atom of that element hydrogen, it would have a mass of 1.01 AMU. If I scale that up to 6.02 times 10 to the 23rd particles of that, in other words, 1 mole of it, I would get the same mass, but instead of it being in AMU, it would be in grams. So 1 mole of hydrogen would have a mass of 1.01 grams. Okay? Same thing for this oxygen here. If you go find oxygen on the periodic table, its average atomic mass is 16.00 AMU. When I go and have a mole of oxygen atoms, that should have a mass of 16.00 grams. Now, if I were to have these together in a compound, I can figure out the molar mass of that compound by basically just adding the molar masses of the atoms that are involved. So let's take this compound here. We're going to figure out the formula and then figure out the molar mass from this. So dihydrogen monoxide has some prefixes in there. Okay, this is between two nonmetals. This is a covalent compound. Okay, and the prefixes are kind of a good tip-off for that. So our prefixes help tell us kind of how many atoms of each element we need here. So we don't have to cancel charges. That makes it a little bit easier. Di is the prefix for 2. Mono, which kind of got cut off by that O on the oxide. Mono means 1. Okay. Hydrogen is H. Oxide is talking about oxygen, which is O. So my formula for dihydrogen monoxide would be 2 H's and 1 O. In other words, H2O. It's water. Dihydrogen monoxide is just water. Okay? Fancy way of naming it, kind of technical way. So if I wanted to figure out the molar mass of dihydrogen monoxide of water, I would just need to add up the molar mass of all the atoms involved in this. Okay? Just like how I could add up the atomic masses of these things. If I had two atoms of hydrogen and 1 atom of oxygen, and I wanted to know the atomic mass of this whole molecule, of all this stuck together, then I would just take the mass of 2 hydrogen atoms and 1 oxygen atom and add them together, and I would get the atomic mass of this. Okay? In order to get the molar mass of this, I do the same thing because the numbers are going to be the same. The only difference is now we're doing it for a much scaled up version of it. So let's do that. Let's take this right here. And add up the masses of these atoms. So for 2 H's and 1 O, this will be 2 times my 1.01 AMU. For my 2 hydrogens, plus one times my 16.00, which is for my oxygen. And if I add those together, I should get the atomic mass of 1 molecule of H2O, okay? Which should be the same number as the molar mass when I scale it up to a mole of that stuff. So just adding these together, this should come out to be about 2.02, okay, plus 16. This should be 18.02 AMU, atomic mass units. Okay? If I went and had a mole of water molecules all together, one mole of water molecules, I would end up with 18.02 grams. Okay? So the molar mass of water is 18.02 grams for every mole that you have. So you could write it like, let's put these guys over here. That's 18.02 grams per mole. Water has a molar mass of 18.02 grams per mole. Okay, let's try another example. It's going to get a little bit trickier. Let's look at calcium chloride. Calcium chloride. Okay, No prefixes here. This is a metal and a non-metal put together, so this is an ionic compound. So in order to make the right formula, I can't just be like, okay, calcium, that's Ca, and then chloride, Cl, and they'll be fine together. I have to look at their charges and make sure they cancel out. Okay? If they don't fully cancel, then these are not going to be making a happy ionic compound. They're still going to be searching for a way to cancel that charge. So I go look up calcium on the periodic table. It's in the second column, going all the way to the top. It should have a positive 2 charge. Chlorine is in column 17. You go all the way up. Should have a negative 1 charge as an ion. So if I put together one of these calciums and one of these chlorine ions, I'm going to have some positive charge left over. Positive 2 and negative 1 together make a positive 1, which isn't good. Okay? In order to make sure my charges cancel, I can't just have one of these Cl's, I need 2 of them. Okay? That would mean I have 2 of these negative 1 charges to cancel with this positive 2. I can go ahead and erase my charges once they're canceled. And I'm left with the formula here, CaCl2. Okay? To figure out the molar mass of this guy, all I have to do then is add up the mass of 1 calcium and 2 chlorines. Okay? Now again, we could do this in terms of AMU first and then change it over to 1 mole, but we can also just cut to the chase and say, I'm going to be looking for 1 mole of this compound in this lab, so let's figure it out. Let's figure out the molar mass. Okay? So we'll start with calcium. We have 1 atom of calcium in this compound, so we're going to deal with 1 mole of calcium in this case. So we go look up the molar mass of calcium, and it should be 40.08. There we go. 40.08 grams per mole for calcium. Plus, we also need the molar mass of 2 of these chloride ions. So 2 times the mass of this chlorine here. If you go and look up the molar mass of chlorine on the periodic table, it should be 35.45 grams per mole. And then we put this all together. Okay? So 2 times this 35.45 ends up being, let's see, 2 times the 35 would be like 70. 2 times the 0.45 would be 0.9. So altogether this should be 70.90. All right. We're still adding that to this 40.08. Something like that. Okay. So we put those together. And the molar mass of our compound should be 110.98 grams per mole. All right. So what does this mean for the lab? Well, we have 6 compounds. Okay. One of them is going to be this dihydrogen monoxide. One of them is going to be calcium chloride, and one of them is going to be the others that we see here. All we have to do to match them up is look at the molar mass. Okay. In each of these cases, like this guy here, or this guy here, or this guy here, these are all going to be 1 mole of the compound. So if I had 1 mole of water, it would have a mass of 18.02 grams. If I had 1 mole of calcium chloride, it would weigh 110.98 grams. So we're going to be trying to match up these compounds just like we did with the elements, okay? And we have basically these options to work from, the ones we're going to work through, okay? So let's do one more example before we match some of these up. Okay, here's our last example. Potassium dichromate. Again, no prefixes, although it might look like it at first with this dichromate thing. This is a polyatomic ion, okay? And it's a good reason why you have to have these figured out by now, okay? If not, I urge you to go and practice them, okay? Have a polyatomic ion sheet nearby when you're doing assignments and labs and stuff like this, so that way you can catch ones you don't recognize and start building them into your brain, okay? So this is going to be an ionic compound, a metal and a polyatomic ion coming together, okay? So in order to figure out the formula, we're going to have to cancel the charges. So I go and find potassium on the periodic table. It's got a positive 1 charge. Okay. Dichromate, again, is a polyatomic ion, so it's not just straight off the periodic table. Its formula is Cr2O7, and it should have a negative 2 charge. That. Now, like our calcium chloride example, one of these is not going to be enough to cancel with this negative 2 charge. So, we're going to need 2 of these. If I had 2 of these potassium ions, that would be 2 positives canceling out with this negative 2 here. Okay? That would make a happy ionic compound. So, I can get rid of my charges. Okay, now I've got the formula. All I have to do is add up the mass of all of these guys per a mole of this stuff. I just have to find the molar mass of each element, multiply it by how many times it shows up in the formula, and then that should give me my molar mass. So we'll start with potassium. If you go look up potassium on the periodic table, it has a molar mass of 39.10 grams per mole. We have 2 of them in this case. So make sure you're not just adding in the mass of 1 of them. Math of that, plus, all right. We have 2 atoms of chromium here. All right, chromium on the periodic table, you go find it, should have a molar mass of about 51.99. We also have 2 of them. Oh, this is going to be tight. I'm going to have to squeeze this in. Plus. All right. And then our oxygen has a molar mass of 16, just like before. So I'm going to take 7 times 16. It's just 0.00, so I'm just going to leave it there so I don't run off the screen. Okay. You can imagine the 0.00 is there if you really want to. Okay, so all this together should be the molar mass of potassium dichromate. So you take 2 times 39.10 and 2 times 51.99 and 7 times 16. So let's see how good my mental math is. So 39 times 2 should be 78.2. 78.2 plus 2 times 51.99 should be, let's see, 103.98. All right, and then 7 times 16, so 7 times 10 would be 70 plus another 42, so 112. Something like that. All right, so I go plug this into a calculator. Pick your favorite. Got mine right here. So 78.2 plus 103.98 plus 112 gets me a molar mass of 294.18 grams per mole. Okay, so again, how does this help us? Well, in the lab, these samples are each a mole of one of these compounds, okay? So potassium dichromate should have a mass of 294.18 grams, when I have just a mole of it. That happens to match up to this guy right here, what I've labeled as compound D. This has 294.18 grams of stuff in it, okay? And it is 1 mole of a compound. Just so happens to be, it matches up with potassium dichromate. It's got a really nice orange color. Our calcium chloride should have a mass of 110.98 grams if we have exactly 1 mole of it. And that's what this guy is, this compound B right here. Okay. And finally, our dihydrogen monoxide, our water, should have a mass of 18.02 grams when we have just 1 mole of it, which would be this guy right here, compound E, as I have it labeled. Okay, which you probably could get a hint because it's a clear liquid. The only one you could maybe get it confused with is compound A, okay, which ends up being something a little bit different. Okay, so with the ones you have left, we can go and match up those compounds by figuring out their formula and then adding up the molar mass, comparing to 1 mole of each of those compounds. Okay. Now, if you notice that your molar masses don't seem to match up to the masses of the compounds that are supposed to match to, you might need to go back and double check your formula. Okay. If your formula is wrong, you're not going to get the right molar mass, and it's not going to match up. Okay. And sometimes also math errors can just happen inside here. So if you don't get a molar mass that's matching one of the compounds that you expect to, you might go back and check your math, okay? Or even back farther, check your formula, okay? And this is the basics of how we use moles in chemistry, and it will be, again, a huge helpful tool when we do stuff with chemical reactions.